Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Good evening, Chris.
Hello, how are you?
Yeah, very good. What's new in the world of science?
Oh, a very exciting week this week. A couple of interesting things caught my attention, including one which I think has amazing archaeological and also sort of human disease importance, which is that researchers in Israel have managed to unlock the genetic code of a sample of tuberculosis from a burial site 9,000 years old. And no one's ever managed to get DNA from TB 9,000 years old ever before. The closest match was some bones and specimens that are about 5,000 years old, both from Egypt and also from Sweden. So this is the first time anyone's managed to do that, which is pretty impressive. But now they've managed to do this out there off the coast of Israel. It's actually a site which is underwater, which makes it even more impressive. It's half a kilometre offshore, where there used to be a settlement alongside a river, and they scooped up the sediment from the bottom of the sea in this archaeological site, and they recovered the bones of a woman and a baby that had been buried with her, about 10,000 years old, by carbon dating of the sediments.
Yeah.
And then by looking at the bones and finding areas which showed the characteristic changes that we see with tuberculosis, because it produces characteristic what are called erosive lesions. It burns holes in bones, if you like. By spotting those areas on the bones and then getting genetic material out of that area, they were able to pinpoint the DNA from TB. And why this is important is that we've never really understood that much about how TB appeared on the scene, when it appeared on the scene, and genetically how it compared then with today, because this tells us enormous amounts about how people moved around and how the TB that we've got today actually got into us in the first place, and how also a parallel form of TB called bovine TB, carried by cows, how that appeared. Because everyone used to think that TB lived in cows to start with. They then gave it to humans, but this research and other pieces of the jigsaw suggest, in fact, the reverse is true, and that TB first got into humans, and it was humans beginning to domesticate animals around about the time, 10,000 years ago, that this settlement was thriving in Israel. And that's how TB got out of the humans and into the animals they kept, and bovine TB was born.
Crikey, that's absolutely amazing. What a wondrous thing science is. Thank goodness somebody's doing something about stuff and finding all this out. Now then, it's time to ask some questions for you, Chris. This has come from Janet on the internet via email, and she asks, she wanted to know if all the planets rotate as well as revolve. If not, which planets? Good question. Chris?
Yes, the planets do turn, and the rate at which they turn depends upon how big they are to a certain extent, and also what's happened to them during their lifetime. First of all, let's look at how planets form. Well, we think about 4.5 billion years ago, give or take, there was a giant ball of gas and dust in space, and something gave that a bit of a buffet or a push, and it caused it to start collapsing in on itself, and various theories have emerged, and one of them is that there was a giant star not far from where we are now, and this giant star was putting out a huge cosmic solar wind which buffeted this ball of gas and dust and made it begin to collapse in on itself. And as it collapsed in on itself, it began to heat up, and that formed what's called a proto-star. And this began to, because the dust is collapsing in on itself and it's turning, because the dust carries on turning even as it collapses in on itself even more, the material that it began to produce was also turning. And this is called conservation of angular momentum. So you ended up with this big blob of hot gas in the centre, which was turning and spinning, and around it was a shroud of other gas and dust and material, which slowly, initially started off like a shell around the outside of this proto-star, but slowly formed around the equator into a sort of disk, a protoplanetary disk, and then out of that we distilled the individual planets, and including the rocky worlds like the Earth, and then the big gas giants like Jupiter. And the reason that the planets all turn is because the dirt and dust and debris and gas that made those planets was itself turning, and there's no way for it to stop turning. It can't lose that energy, so as it all merges into one big body to form a planet, the planet gains that extra momentum, so it carries on turning. Now that's why all the planets line up in one plane, if you like. If you were to look at the solar system side on, you'd see all the planets in a line in the same plane, but they're all turning, but they're not necessarily all turning in the same direction. And a good example of the planet that bucks the trend is Uranus. And this is actually turning on its side. It's as though the planet's been twisted sideways. And this has led some researchers to suggest that at some point during its development, there was a huge cosmic collision, maybe between two planets that were in the process of forming, and this is what knocked Uranus off kilter. The other possibility is that it's just the resonances, what are called resonances. When the planets were forming, the gravitational tug and pull of the early solar system dragged certain planets around, and as a result it pulled Uranus over and it ended up turning around on its side. I don't think we've got any closer to the answer other than some clever maths at the moment, but there's the answer. Pretty much they all turn, they take different times to do it, and some of them turn sideways.
Absolutely, right. It's interesting, actually. We had Andy Green, who's the director of the Stardome Planetarium, in the other night, and he brought a meteorite in, and I was absolutely gobsmacked at how heavy it was, and it was only about 4 inches by about 2.5 inches deep, but it was an iron one. It was really, really heavy. It's just fascinating.
Yeah, that's right. And the interesting thing about meteorites is that they hold really our cosmic history inside them, because they're almost like miniature time capsules, because a lot of them, in fact, an enormous number, the vast majority, date back to the vestiges of the solar system when it was first forming from that gas and dust. And many of them have been bobbing around in space for 4.5 billion years until they land. Not all of them. In fact, we do get bits of other planets that land here on Earth, because when giant impacts strike other planets like Mars, for example, they can jettison bits of the surface of Mars up into space, and it then travels through space until it ends up on a collision course with the Earth and then lands here. And lots of those meteorites get recovered from Antarctica, because it's very easy to spot them because they're black up against the white snow. And also there's a sort of ice conveyor that goes on in Antarctica, where the ice gets formed, it sinks down and then comes back up again, and so this carries anything embedded in the ice, like the black meteorites, with it, and they all end up sitting on the surface, and periodically scientists go to Antarctica and pick them up.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Let's go straight away to the phones and say good evening to Agnes. Hello, Agnes.
Hello. I'm wondering if, having had 2 blood tests, the reason having within 10 days, I take thyroxine. It's only in the last few years I've taken thyroxine tablets, 1 every day. I've been stepped up from 50, whatever it is, micrograms tablets, to another 20, up to 75. Being curious and it being myself, I want to know what's going on. I wondered if, having had the blood test so soon, one 10 days later, had it any detrimental effect.
Chris, what do you think?
Well, thanks, Agnes. Very interesting question. Thyroxine is the body's metabolic rate-determining hormone. It's basically how your body sets its thermostat. Thyroxine is produced by the thyroid gland, which you find in your neck. And it's produced using iodine, which people used to get deficient of in the early days when they didn't have iodine in salt and lots of other things. And so there was a condition called Derbyshire neck. And people who lived in Derbyshire were prone to get a goiter, because if you don't have enough iodine in your diet, the thyroid can get bigger than it ought to, and that produced a swelling. But these days we're much better at giving people enough iodine, so that's very rare. And more common in women actually, is the thyroid becoming underactive as you get older. And if you have an underactive thyroid, you can spot that, because you tend to get quite tired quite easily. People might say that they're putting on weight for no apparent reason. You also feel cold, and you can feel quite lethargic and not feel like you want to do anything. And people sometimes say that their hair can get a bit thin and their skin can deteriorate. Luckily, it's very easy to treat, because people can be put on a simple tablet, which is thyroxine itself. You just give people the hormone they're missing. Usually a small dose, 50 micrograms is enough, and this normally makes people feel much better. Now, how do we actually monitor whether we're treating people adequately or not? Well, the answer is you do a blood test. Now, you could just test for the thyroid hormone in the blood, but another way of doing it is to look for the chemical that normally switches the thyroid on. And this is a hormone called TSH, or thyroid stimulating hormone. And this is produced by the pituitary gland in the brain. And the brain basically tastes your blood to see how much thyroid hormone is there.
Really?
And if there's not enough thyroid hormone, it produces some of this TSH, which travels in the bloodstream, goes to the thyroid in the neck, and says, increase how much thyroxine you're making. And so there's a sort of feedback loop where the thyroxine then comes out of the thyroid, goes to the brain, and shuts off the supply of TSH. So if you measure the amount of TSH in the bloodstream, you can tell whether or not the body thinks it's got the right amount of thyroxine on board. So you do periodic blood tests to see if people are being adequately treated. And it's very simple, it's very routine, but if the thyroid doesn't keep up quite enough, then the TSH level can go up, and this means that doctors know to maybe prescribe a little bit more thyroxine in order to bring you back into kilter. So there's the answer.
Oh, that's a very good. I haven't put on weight, my skin is all that, and I feel terribly healthy.
Yeah, that's very good going. All I can say is, Agnes, I think you're doing very well, but that means that also you're being treated very well, so you're on just the right dose. So.
Oh, thanks very much.
Bye-bye.
That's very detailed. Thanks very much.
Bye-bye. Agnes there. Now, Julie has sent a text in to say, why is it that rain clouds, Dr. Chris, are dark in colour?
OK, the reason clouds are dark is because clouds are made of water, and the more water they have in them, the darker they are, because the water particles and ice crystals and things tend to soak up light as it goes through, and this makes them look darker, because the denser something is, the more light that gets reflected back out into space, and therefore the less light comes through the cloud, and therefore it looks white. It's a bit like if you look at a mountainside, fresh snowfall, it looks white because the snow is reflecting the light that lands on it. Clouds look white because they're reflecting the light that hits them back at you. But if it's dark, because the clouds are so dark and dense themselves, then they're reflecting lots of light from the sun hitting the cloud on top back into space, so not much light's getting through to the ground, therefore not much light is hitting the cloud anyway, therefore it's not being illuminated very much, therefore it looks darker. So the thicker and heavier the cloud is, the darker it is. And since heavy clouds are full of water, that usually means rain, so a big black cloud usually means a deluge.
Excellent. Thank you very much, Dr. Chris. Time to get back to our Naked Science Uncovered. You can ask the Naked Scientist. We have a caller on the line, I believe. Is it Ted?
That's correct, yeah.
Hi, Ted. What's your question for Dr. Chris?
Dr. Chris.
Hi, Ted.
I like honey, and honey tends to be very sticky and difficult to, and I want to know why the bees are very, very delicate, and the wings are delicate. Why don't they get all stuck up in their own honey?
I think they probably do at some point. The reason that honey is so sticky, of course, is it's full of glucose, sugar. And when the bees are handling it, in fact, the way they make honey is that they secrete various things from their mouth parts and other bits of their body, actually, with the bee secretions, which they use to manipulate and break down the sugars so that they make the correct composition of honey. And the bees are very delicate in how they handle it. They feed the honey itself by eating bits of it and then regurgitating it to young bees, in other words, the larvae and other cells in their colony. And so, as a result, they don't end up making a mess. It's not like a toddler or a 2-year-old who, if you gave them a pot of honey, it would be everywhere. But bees, luckily, are a little bit better trained and a bit better behaved.
Yeah, it puts you off, really, when you say that, don't it? Now, organic honey, somebody, a good friend of mine, bought me some organic honey. What would be the difference between organic honey and, supermarket honey?
Well, in order to fulfil the requirements of being organic, it means that the crop, or whatever it is grown in the absence of any kind of additives like pesticides. That wouldn't be good if you wanted to rear bees anyway, if you were killing them all with pesticides, would it?
Right.
But in other words, when you make the honey, the bee would be preying or using plants and plant nectar and pollen sources, which were plants that were not being treated by things like pesticides. So in other words, you've got to guarantee that wherever the bees are collecting their raw materials to make their honey, they're not being exposed to chemicals.
So how far would they travel? How could they guarantee that they're not been in, like, 2 fields away or something?
Well, very tricky, because a big bee, like a bumblebee, even a honeybee, has a range of many miles. A bumblebee can go 10 miles away from its hive, and it will find its way back perfectly. So the answer is bees have a very big territory, and once they find a good source of food, they go and tell all the other bees by doing something called a waggle dance, which is, the waggle dance was decoded a few years ago, but bees fly into their hive, and they then perform on this sort of hive dance floor and the number of times they turn around indicates a certain distance that the bees have to fly. The direction they turn in tells the other bees what direction they have to fly in, etc. And that's how all the bees find all the best food sources. So you've got a very good point. The bees could fly into an area where it's not necessarily organic, and it's up to the people who are making the organic honey to prove that that's the case, and that the bees haven't trespassed into non-organic food sources.
That's interesting, because I like my beer as well as my honey, yeah? And there is a beer called Waggle. I mean, it's got honey in it.
Well, there you go.
Like me.
Where
can I get some?
Yeah, honestly, yeah.
Ted, thank you very much indeed.
Brilliant. Yeah, thanks very much.
Thank you, bye-bye.
Okay, bye.
Bye-bye. Let's get to the dark side of the moon right now, Dr. Chris, or the dark curve, if you like. Why is the dark curve of the moon seemingly on the wrong side?
Okay, it all comes down to how the moon actually appears in the sky and why it appears the way it does. So when the moon goes around the Earth, it takes about a month for the moon to complete each orbit, because the moon is actually orbiting the Earth quite slowly. And as a result, as it goes around the Earth, it's also turning very, very slowly at just the right rate, so it always shows us the same face. That's why there's a light side and a dark side of the moon. But the illumination of the moon is what determines what we see in the night sky. It's not because the Earth is getting in the way of the light coming from the sun and that's casting a shadow on the moon. Lots of people think that. That would actually be an eclipse, and that's not what's happening. A good way of thinking about this is if you had a broomstick with a football on the top of it in your garden, and you pretend that's the moon, and you ask someone to shine a torch on the football, and that's the sun, and you then stand and look at it from various points in your garden, what you'll see is that the face of the ball that's illuminated, when you're standing where the torch holder is, will look completely illuminated, and you'll get a round ball. That's a full moon. If you go and stand at 90 degrees or off to the side of the football, you'll see that you get something resembling a half moon, but you'll see that the edge of the moon that's illuminated that you can see has got a curve going opposite to the curve of the Earth, because the moon, it's down to the direction the light is coming from the sun. It's not the edge of the Earth that you're seeing, and it's just to do with how the light's hitting the surface of the moon. So that's why it looks like it's wrong, but it's not wrong because it's not an eclipse. It's not the edge of the Earth you're seeing. It's actually the edge of the light hitting the moon.
Good one. All right, this time from Jeff, an email. Hello, Sue. Yesterday spoke about psoriasis. One question for Dr. Chris. Why does ultraviolet rays be beneficial for skin complaints like mine when we are told to stay out of the sun because of the risk of skin cancer?
Yeah, it's a tricky one. Psoriasis, for people who are not in the know or don't fortunately suffer from it, is a condition of too much skin growth. So in various patches on the skin, you get these areas where the skin very rapidly accelerates its growth. So instead of taking a long time for the cells to make their way from the base layer, where the stem cells are, out to the surface, and this normally takes a number of weeks, it can actually do it in a number of days. And this means you get these scaly patches, which are often a salmon pink colour, and they're very flaky. They build up, and it usually happens on things like the elbows, back of your neck, scalp, hairline. And the cells there seem to be growing very, very fast. And what scientists and doctors have found is that one treatment for psoriasis is ultraviolet light. And this is based on historical reports when people used to go to the seaside on their summer holidays, get exposed to a dose of sun and sea, and the result was that their psoriasis got a lot better. And people realised it must be something to do with the UV exposure. And now a standard treatment for psoriasis is to give people a chemical called Psoralen, which is a photosensitizing agent. This is something which gets into the cells in the body, and it gets turned into a more toxic chemical when it meets ultraviolet light. And when you put people who've taken this drug into ultraviolet light, it kills cells that have got enough of it in them. And because the skin is being exposed to most of the ultraviolet, it kills cells in the skin. And this helps the psoriasis to be put under control, because the psoriasis takes up more of the drug than the healthy tissue does. But the bottom line here is that ultraviolet is bad for cells and kills them, and because you've got too many cells growing in psoriasis, it kills more of the bad cells, and so you end up with a resolution or an improvement in the condition. But the flip side of the coin is that you will have an increased risk of all of the attendant damage done by ultraviolet, which is the price you have to pay for the improvement in the psoriasis, and that means you have ageing of the skin on things like the face, and also you have an increased risk of skin cancer. So unfortunately that's the toss-up. It's an unpleasant condition, and it's unfortunate of those people who have to put up with it.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.